In part 2, we are going to talk about the exponential function. So now get ready to do some math. Before we get to the actual number, suppose you are offered two boxes, a box A and box B. Like each has a function, or has an amount of money you will get on day X. Like which box will you choose? Like, and the way this works is usually I should review that one at a time. So let's say the boxes 10x, 10x and x squared. Okay, which one would you choose? Which one should give you more money I should say that in the long run. In the long run. So think of x as a high number like 1,000 or 1,000,000. I don't think we live that long, but it's very high number. So for instance, 10 times x and x squared. Like if you just take a look at it at glance, like and for instance for the first pair, like on day 1, 10 times x gives you 10. And because it's 10 times the number, but x squared only gives you 1, because 1 square is 1. So you say, oh, that doesn't look promising. Like you would rather get 10 times x times x. Let me choose a better color. Yeah, 10 and 1. On day 2, 10 times x gives you 20. But x squared gives you 4. Okay, so it seems to be getting started, but still far away from 10 times x. For 3, you get 30 and 9. Still, the first box looks more promising. Like on day 4, you get 40 and again 16. And so on and so forth. And if you just take a look at the small samples, it would seem that the first box is almost always better. Like almost always. But of course, your first intuition, again, almost always wrong. On day 10, like on day 10, you would get 100 for the first box because 10 times 10 is 100. But also 10 square is also 100. So on day 10, they match. On day 11, you get 110 for the first box and 121 for the second box. And if you have enough time, or if you can graph this, you can see that eventually, or like even starting from day 10, 11, and from there on, it will beat the first box. So even though it looks better in the short run, like eventually, the second box will give you a higher return or higher profit or free money. Yeah, so the answer is B. But what if we change the number to 10,000 times x versus x squared? Would you still choose the second box or the first box? Like, because if you take a look at the first box, like even if at 100 or 3 months, then the first box would give you 10 million. Oh, sorry, 1 million. Yes, exactly 1 million. Versus the second box, which gives you only 10,000. So again, it seems like the first box would win. But eventually, if you have enough time, and in this case, if x is 10,000, then both box A and box B will give you the same amount of money. And after that point, box B would always beat box A by a pretty large margin. So again, you should almost always pick the second box, the x squares versus x times any number. And you can see the trend, like if it asks you for x squared and x cubed, then again you should, if you have enough time to wait, you should pick the block where the exponent is higher. But the next question is, what about these two functions? And so this is a quadratic function, or a polynomial that we talked about already. But this is a new function. This is the exponential function. You compare these two, Actually, for this one, it's easy to see because if you just make a table to compare x squared and 2 to the x, it will be pretty clear that they are the same here, but the first one seems to beat that by a little bit. They are equal on the fourth day, and then on the fifth day, the second box is better. The box B, the exponential one. 24 on the seventh day, you get 49 versus 178, and now you can see that it only takes a week for the second part to beat the first one by noticeable amount. And then the interesting thing about this function is that even if you compare these two functions, x to 1 million versus 2 to the x, even though this number is very, 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 very small, the thing is by the definition, by the some math we don't have enough knowledge to prove, but interestingly, this would beat in the long run. It would beat eventually. This would win eventually. Eventually win. The fight would eventually give you more money. And so that's the power of exponential. Even though you compare that 2 to the x, the small number 2, like 2x to the 1 million. Pretty large number. That's very, very difficult to imagine, but still, exponential will beat that eventually. And so that's the extent of the exponential function. It's something that grows faster than any kind of polynomial. And yeah, that's a graph, of course. And if you compare 100 times x to x squared to x to the 4 to 2 to the x, right there, at the start, like if you show it in, there seems to be like kind of like competing. Like for instance, for the first point, like this purple beats, the red one beats everything else, like it's 100. When x is 10, like we have the green one, it gets higher. When x is 100, like we get the purple one, 10 to the 30 versus 10 to the 8. And finally, 10 to the 301, which is impressive. And also, even if like if you compare the linear function like to the quadratic, like you could see that they beat eventually. I think that's quite fun to not that point, but somewhere far away. And so that's the comparison between the growth of different functions. So let's get back to math. Like these are all just intuition of what it looks like and why we study it, but we have to eventually study that. So the basic definition of exponential function is similar to what we define when we first learning about the addition in elementary school, right? And then we learn about multiplication. Then we define the multiplication to be a repeated addition. And you repeat addition. So a times m mean you add number m a times. And that's how you define the multiplication. And likewise, like we define the exponential by using the repeated multiplication. Repeated multiplication. Just keep multiplying the same number. Multiplying the base over and over for a times. That's a basic definition. And you might notice that it's kind of like isn't consistent. That is like this sometimes. Like where for multiplication you have a to the left and m to the right. But for the exponent, m is at the bottom and a is to the top right. They are kind of flipped. And that's what we use nowadays. So yeah, you can use the definition to compute these numbers. Like for a, 3 square by definition is 3 times 3, which gives you a 9. Or in B, 5 to the power of 3. Or maybe I should write how to read it. Yeah, I forgot to write how you read this term. Okay, there it is. M to the power of A, which is long. Usually you could say M to A, but again that seems vague or ambiguous. So we add the word to the power of to make sure that we understand that we are talking about exponential functions. So this will be 3 to the power of 2, 5 to the power of 3, 2 to the power of 10, and 7 to the power of 1. You will see in a moment what to do with that. So 5 to the power of 3 means you multiply 5 3 times. And if you have your calculator, or if you can do it in your head, you get 125. For C, 2 to the power of 10, it means you multiply 2 10 times, 5, 6, 7, 8, 9, 10. Multiply 2 10 times, you get, again, if you have a calculator or if you know this number by heart, you get 1024. And lastly, 7 to the power of 1. It asks us to multiply 7 1 times. So there is only one term, and 1 means you don't have anything else. So it's kind of, so the answer is 7. It is kind of weird, right? So you multiply it 1 time, so you don't multiply anything. That means you have one term, and that term happens to be the answer. Yeah, but that's how this works. So that's the exponential functions. And there's a slightly a different notation, which personally I don't use it. To be honest, I don't use this term as an exponential function, because in real world, usually this is combined with other terms. Maybe they have x, maybe there's constant, and there could be many things to follow it. But for the sake of simplicity, as if this is the first time you learn about this exponential, like we let an exponential function be a function of this form. So this is a times b to the x. Oh, and actually b, I should say that b is a real number. Oh, b is oh, that should be b. My bad. B is for positive real number, but a is any real number. Like we have 2 to the x. Yeah, just a b itself, like where a is 1. There's no coefficient, or there's no multiplier in the front of that. Or look, we have 3 times 10 to the x minus 0.01 to the x. And be careful when you read or write or interpret this kind of statement, right? Because if you write this way, that means the number the minus sign is alone, and that power of x only applies to the number 0.01. Like this is different from this formula. If you plug -1 into the function, like into the number, and so this is a single number, and you raise the whole number, the whole negative number by the power of x, that will give you something different. But at this point, like b or the base, there has to be positive real number. So in this case, you could write it. It could be a function, but for the sake of simplicity, we don't study it yet. So let's assume that b, like the base of this function, is always positive and real. And yeah, you can have positive number that is smaller than 1. In this case, you have 2 over 25, which is like 0.08, I think. But yeah, that's there. And once we have the function, then you can just write functions. Just graph. Like before, you can conclude something interesting about the graph. So let's just take a look at this graph, these 4 graphs, and see if you can draw any interesting. conclusion about the graph. Or if you have if you can open Desmos yourself, I recommend you plug in these values and maybe zoom in the graph yourself, and maybe click on dots or points to see. So there are three interesting characteristics or properties of this graph. First, they all meet at this point. Interestingly, if the function is just a base to the power of x, if there's no exponent or there's no coefficient, there's no constant in front of that, then they all meet at this point. What is this point then? If you take a look at the graph, this is where x is 0, as you can see from this. The x value is 0, and the y value is 1. And because 2 is here and this is halfway, so it's 1. What that implies is that, if you raise any number, if you let x be 0, then y will be 1 for any base. So this for the red graph, when the red graph passes through this point, which means if you plug in x equal to 0 into the function, the value of y would be 1. So 2 to the 0 is 1, 3 to the 0 is also 1, 4 to the 0 is also 1, 10 to the 0 is also 1. They are all the same. So that's one feature you can conclude just by looking at the graph. Second, let's take a look at the right hand side. If you take any random point, let's say this point, and then if you draw a straight vertical line upward, then you can compare the values of these four graphs. The purple one is on top, and this is purple, so that means when the value is positive, if you look at the right half of the graph, then this value will be higher than the green one. That's on x. It should be 4 to the x. And the green one is above the blue one, so it's greater than 3 to the x. And lastly, the red one is at the bottom. It's smallest. So if x is positive, if you look at the part where the x value is positive, then the graph is arranged in this order. Which tells you that the higher the base is, the better the graph. Which is intuitive. If you start at 1, and there are two groups. The first one multiply each time by 2. The second group multiply each time by 3. And then of course eventually, even at the start, 3 to the x, or when you multiply 3's repeatedly, it should give you a higher number than if you multiply them by 2. But lastly, the third, actually there are 4. The third observation is that if you flip it to the negative part, right, then everything is reversed. Meaning that the red graph, 2 to the x, is actually higher than 3 to the x, which is the blue. And then the blue is above the green, and the green is above the purple. So when x is negative, everything is flipped. But we will see in a moment why. But for now, to not spoil you of this property, now if you are given a graph, let's see what you can get eventually. And finally, if x is very small, x is not very small, but if x is a big negative number, so that means if you continue to the left, like forever, if x is a big negative number, then the value will be close to 1, close to 0. Like for any base, even if it's base 2 or base 3 or base 3 or base 10, and everything will get close to zero. That's how you can read. That's what you can read from the graph. And in calculus, there's the notation of limit, but of course we don't touch that here. And so these are all the observations you can take just from looking at the graph. Without even knowing what this function does, you can see. Oh, sorry. There's one more thing I should also mention first, that the function is increasing. Increasing. Meaning that if you have 2 points, one to the left and one to the right, then the point on the right would be higher than the left always. It doesn't matter what the base are. If as long as the base are, I should also say that the base must be at least 1 for this to happen. Then we have this graph, increasing graph. So that's the basic comparison we can get, without getting to the real math yet. And next we have by the definition, we talk about these numbers as you multiply something by some number. You multiply 3 times, you multiply 2 10 times, you multiply 7 1 time. But what if you are asked to multiply some number by half the time? Can you multiply a number half the time? I don't think you can, right? Yeah, usually you can. But if you go back to take a look at this graph, you may notice that actually, this graph works for any x. This graph works for any value of x. So x doesn't have to be a positive integer at all. X can be negative even, or x can be any fractions, any real number. X can be square root of 3. X can be square root of 3. X can be pi. X can be 0.1. We can always compute that. But yeah, there must be a catch, because you cannot compute those numbers by multiplying the base by that number of times. Like you cannot multiply 2 by pi times. Like that doesn't make sense anymore. Like there's a math behind that. But we have to start from from fraction. What if we multiply something by a fraction? So in this case, we have like half of the number, but not half in the sense that you divide it by 2, and not this half, like half in the sense that you multiply them. Like how would you compute that? But yeah, maybe let's first get back to half a number. Like what does it mean for a number to be a half? It means we can add another copy to get back to the origin, which is m. And so half, this half corresponds to the addition. Likewise, if you have a number that is half the power, and since the power is about multiplication, it means if you multiply that by another half, you get back to m. And so that's how we define a number that is raised to the power of a half. Right? And by the same analogy, you can repeat that for any number. Oh yeah, but before that, let me finish this first. Right, so once you define, once you do that, you multiply two things, you get back to m. And if you multiply two numbers together, that means you raise it to the power of 2. Right, and lastly, we do have a notation for that. Right? If something square is a number, right, then that number is the square root of the thing on the left, on the right. And so this is the reason why a number to the power of a half is a square root. Because if you square it, you get back to the number. And likewise, we can draw the same analogy to any power. m to the power of 1/3 mean if you multiply the 3 copies of that, you would get back to the original m. And of course, there are 3 copies, so it's to the power of 3. And a number to the power of 3, we can reverse that and get, by definition, the root. So that's how the rational fractions work, right? But also that this is not the only way. This is not the only fractions, right? Because sometimes you could get, let's say, m to the 3/4. What is m to the 3/4? Again, we're gonna have properties soon. But just at this point, I suppose we are learning this as an entirely new topic. And we want to explore how should we define because usually in math, you are given the correct answer first and asked to repeat that over and over. Here we don't know what the answer is, so we try to discover, at least draw the analogy from what we already know before. What should be m to the 3/4? That's some kind of difficult, right? 3/4. You multiply a number by 3/4. What is that? What's the 3/4? But again, just like number. If you think about 3/4 of a number in terms of addition. So let me write this way. 3/4 of a number is actually 3 copies of 1/4, which we can write as 1/4 plus 1/4 plus 1/4. And this is what we have for addition. Sometimes if these two numbers doesn't interact well, sometimes you have to split them into 2 different parts. And this is how you would do it. And so you take that as a multiplier or as a number of copies. And there are 3 copies of what? 3 copies of 1/4 m. So that means similarly, if you try to, follow this step, then we have 3 copies of 1/4. But again, since the copies represents the multiplication, then we have 3 copies, mean we have that number to the power of 3. Or in other words, it's m4 times m4 m to the 1/4. So that's what we have. And you might or you could use the root. That's gonna take a while, but sorry. It could be the over the 4th root of m. To translate that into something that we are at least more familiar with. And eventually you can actually express that as the 1st root of mq. So that's how you draw the analogy from this new topic to something that we hopefully already know before about the root. So yeah, this is something that we just try to guess based on the definition and based on the analogy between powers and multiplication. And of course we are correct because I thought that. But yeah, using these observations, and eventually we can actually prove it that the end root is m to the 1/2. They are the same thing. They are just written in 2 different topics. And this is viewed as the root, and this is viewed as the exponent. And many times it is useful to go back and forth. Sometimes the root is easier to think about. If you have m to 1/2, what is 1/2, right? So square root of m is easier to visualize. Like if you have a square that has the area m, then each side would have length or width of square root of m. That's how you visualize the square root. Right? But again, multiplying a number by a half, but that doesn't make sense. And so that's the property. And next we have but if we have a over b, we can rewrite it as m to the a, and then take the bth root of that number. Or you can take a b root first and raise the power to the a. Whatever works best for you. Okay, so that's the basic definition, like how we define that, and also how we can extend like the notion of the notation of multiplying something over and over, like to multiplying something by a fraction. Just get to the a fraction, a half, or a third of a number. And that's the second part.